Hi, this is Seethalakshmi, Associate Professor, PG and Research Department of Physics, Seethalakshmi Ramaswamy College, Tiruchirappalli. Now, I am going to talk about semiconductors and diodes. You know well, the materials are classified into three categories: conductors, insulators, and semiconductors. First one, conductors. In general, all metals are good conductors. The purpose of conductors is to allow electrical current to flow with minimum resistance. For example, copper, gold, silver, iron, etc. The next one, insulators. Insulators are used to prevent the flow of electricity. Insulating materials such as glass, rubber, plastic, polyethylene are also called dielectrics, meaning they can store charges. Dielectric materials are used in components like capacitors, which must store electric charges. Then semiconductors, materials which are neither conductors nor insulators, that is, whose electrical properties lie between conductors and insulators. That is used in components like transistors. Here, the semiconductors are given as silicon and germanium. Then types of semiconductors. We all know the semiconductors are classified into two: intrinsic semiconductors and extrinsic semiconductors. First one, intrinsic semiconductors. Intrinsic semiconductors are pure form of semiconductors, that is, there are no impurities added in these conductors. The number of free electrons in the conduction band is equal to the number of holes in the valence band. Conductivity of these semiconductors is low. Electrical conductivity is a function of temperature alone. For example, crystalline form of pure silicon and germanium. The next type, extrinsic semiconductors. An extrinsic semiconductor is a semiconductor that has been doped, that is, into which a doping agent has been introduced, giving it different electrical properties than the intrinsic semiconductor. The number of electrons and holes are not equal. There is excess of electrons in N-type semiconductors and excess of holes in P-type semiconductors. Electrical conductivity is high, and the electrical conductivity depends on temperature as well as on the amount of impurity doping in pure semiconductor. Examples: arsenic, antimony, bismuth, aluminium, etc. are doped with the germanium and silicon atom. Then how to improve the conductivity by means of doping? Here, the doping involves adding dopant atoms to an intrinsic semiconductor to make semiconductors better conductors, add impurities, that is dopants, to contribute extra electrons or extra holes. Here, the dominant carrier concentrations in an extrinsic semiconductor classify it as either an N-type or P-type semiconductor. Here, elements with 5 outer electrons contribute an extra electron to the lattice, and elements with 3 outer electrons accept an electron from the silicon, that is acceptor dopant. Then what are P-type and N-type semiconductors? Here, the semiconductors are classified into P-type and N-type semiconductor. First one, P-type. A P-type material is one in which holes are the majority carriers. That is, they are positively charged materials. And N-type semiconductors. A N-type material is one in which electrons are the majority carriers. That is, they are negatively charged materials. Here the PN junction diode is given. Here in this PN junction diode, the P-type material and N-type material are combined together, and we know the P-type material is having majority charge carriers as holes, and the N-type material is having majority charge carriers or electrons. The holes and electrons are combined together in the origin, that is space charge region. Then diodes, electronic devices created by bringing together a p-type and n-type region Within the same semiconductor lattice, it is used in rectifiers, and it is represented by the following symbol, where the arrow indicates the direction of positive current flow. And here in the schematic diagram, the triangle represents positive and bar indicates negative. The characteristics of diode. The diode always conducts in one direction. Diodes always conduct current when it is forward bias, that is, it is having zero resistance. And diodes do not conduct when it is reverse bias, that is, it is having infinite resistance. Forward bias and reverse bias. In forward bias, connect positive of the diode to positive of the supply, negative of the diode to negative of the supply. And in the case of reverse bias, connect positive of the diode to negative of supply and negative of the diode to positive of the supply. The forward bias and reverse bias connections of PN junction diodes are in the figure. Here, in forward bias condition, the positive voltage placed on p-type material, holes in p-type move away from positive terminal, electrons in n-type move further from negative terminal. Depletion region becomes smaller, that is, resistance of device decreases. Voltage increased until critical voltage is reached. Depletion region disappears, current can flow freely. But in the case of reverse bias of PN junction diode, positive voltage placed on n-type material, electrons in n-type move closer to positive terminal, holes in p-type move closer to negative terminal. Here the width of depletion region increases. It allows current, it is essentially zero, that is small drift current. Here VI characteristics of PN junction diode is drawn. The forward characteristic of PN junction diode in the first quadrant and the reverse characteristics of PN junction diode in the third quadrant. Here in this graph, forward voltage is taking along positive x-axis and forward current is taking along positive y-axis. The forward characteristic curve is drawn. Here the forward voltage is 0.7 volt for silicon and 0.3 volt for germanium. These silicon and germanium are semiconductors. And in the case of reverse characteristic curve, the breakdown voltage is noted, example 50 volts. Thank you for watching.